In the previous video, we defined the directional derivative, and we were able to interpret it in terms of the difference quotient and a limit. And we saw at the end that we could use that limit definition to compute the directional derivative of functions in a particular direction. But we also saw that even with a very simple function, a very simple vector, that calculation was a little tedious. And you can imagine that would be even more so if more complicated functions are involved. And so what we're really going for is to try to find a way to efficiently compute this derivative and not have to go through and compute that limit definition every single time. And we can kind of figure out a way to do this by going back to how we developed the directional derivative and realizing one of the keys there was the chain rule. But in that limit definition, there is no real presence of the chain rule. And so we can use the chain rule to sort of come up with a better, more efficient way of computing this directional derivative. Right? And so just to set the scene of what we're doing here, again, we have this function f of xy. We want to compute the directional derivative of this function at a point AB in the direction of some unit vector u with components u1 and u2. And once we have this unit vector, we have this curve r of t, which is the line through this point in the direction of u. So it was a plus tu1, b plus tu2. So this is our line that goes through our point in the direction that we want our directional derivative to indicate. So our directional derivative, by definition, when we defined it, is the derivative of f with respect to t evaluated at the point AB. Right? And so we can just go through a couple layers of computing this. So we did use the chain rule in the previous video to compute df dt, and we saw that that is equal to del f del x, and this would be evaluated at the point AB. That's a function of two variables. We'd multiply this by dx dt. Now this has to be evaluated at the point t equal to 0. It's a function of the one variable t. And the point t, if you notice in the function r above, we get the point AB by letting t equal 0. Right? And then we have to add to this del f del y, evaluated at the point AB, times dy dt, evaluated again at the point t equals 0. Right? Well, if we go through here, this first object over here, del f del x, evaluated at AB, is another way of saying I want the partial of f with respect to x evaluated at the point AB. Dx dt, evaluated at t equal to 0, if we go up and we compute the derivative of the function x, which is a plus tu1. Right? This is our value of x. This is our value of y. So if we compute the derivative of x and evaluate it at 0, we will get u1. So this is just that times u1 plus del f del y evaluated at AB is just the partial of f with respect to y evaluated at AB. And dy dt evaluated at t equal to 0 is just the constant u2. In fact, the evaluating at 0 for the derivatives of x and y don't matter because both derivatives are constants. Right? And so we have f sub x of AB times u plus f sub y of AB times u2. And when we look at this, we notice that we could write this as a dot product of two vectors. So we could write this as fxab, comma fyab, so the two partial derivatives evaluated at our points. and we take the dot product of that vector with the vector u1, u2, which of course is just our unit vector u. Right? And so we know this vector here is our u, and so that gives us this vector here, and this is a pretty easy vector to come up with. If I have my function f, all I have to do is compute the partial derivatives with respect to the variables and evaluate it at the given point. And so we're going to give that vector, it's going to obviously important here, we're going to give this vector a name. So our formal definition here of that vector, we're going to call it the gradient vector. So the gradient vector of a function of two variables, f of x, y, is the vector that we're going to denote with an upside down triangle of f of x, and it's going to be the partial derivative of f with respect to x, comma, the partial derivative with respect to y. Right, so the upside down triangle is often called the gradient symbol. And so this is exactly the vector that we needed to compute the directional derivative, and we'll do that in a second. But first, I'll just mention here, this extends naturally to any number of variables. And it extends in the very obvious way. Right, so if I have a function of three variables, let's say f of x, y, z, then the gradient vector of f, y, z is the partial with respect to x, the partial with respect to y, and the partial with respect to z. And if we had a function of four variables, I'm not going to write this down, but a function of four variables, the gradient would be a vector with four components, and the components would be the partials with respect to those four variables in the order that they're indicated, and same with 5, 6, 7, or 823 variables. And so the main usefulness of the gradient vector, although it will appear several times throughout the remainder of the course, its main use, at least right now, is the following theorem. And so the theorem says this, it says assuming that the directional derivative in the direction of u exists, so assuming that directional derivative exists, right, we have that this is actually equal to the gradient vector of f evaluated at AB, dot product with the vector u. Right? And so this is actually, the directional derivative is actually quite easy to compute. We just find the gradient vector, which amounts to finding partial derivatives, and we take a dot product of that vector with the unit vector u. Right, just like the idea of the gradient vector, this theorem can extend to functions with more than two variables in sort of an obvious way. And so if I have a function, we'll call it f, and let's say it has n variables, x1 through xn, and this is a function which is differentiable at a point a1 up to an, so a point in n-dimensional space. And I have a vector u is a unit vector with n components. Then the directional derivative of this function, f, evaluated at a1 through an in the direction of u, is simply going to be the gradient of f, evaluated at the point dot the unit vector u. Right, so notice in this context, u is a vector with n components, and therefore this dot product is defined. Right, but it works exactly in the same context in any number of variables. There's no difference other than the length of the dot product. So let's look at an example where we use the gradient to help compute the directional derivative. Right, so we want to compute the derivative of the function f of xy given by the formula x squared y minus e to the xy at the point 1, -1 in the direction of vector 2, 3. So to solve this problem, what we need to do is we need to find a unit vector in the given direction. We need to find the gradient vector of our function at our point, and then take the dot product of those two vectors. All right, so let's start by start by finding the unit vector in the direction of v. Right? And so the first step is we do need to find the magnitude of our vector that we were given, 2, 3. Right? And that's just going to be the square root of 2 squared plus 3 squared, so the square root of 4 plus 9, which is the square root of 13. So this vector is just the square root of 13. Right? And so a unit vector in this direction, which we can call u, is just going to be 1 over the square root of 13 times our vector. Right? Now, for purposes of directional derivatives, and we'll see this later, it's actually beneficial to keep the scalar out front like this instead of distributing it through the vector and actually computing it. And we'll see again why that's useful later on using products of dot products when we get to that point. Right, so now we have the unit vector. The next thing that we need to know is we need to know the gradient vector of our function. And so our gradient vector is just the first component is the partial derivative of our function with respect to x. So if I look at my function f and I differentiate it with respect to x, we're going to get 2xy minus y e to the xy. All right, so that's my partial with respect to x. I'm then going to take the partial with respect to y, and when I do that, we get x squared minus x e to the xy. Okay. So there is my gradient vector. At a general point, for our computation here, we're going to want to find the gradient vector at the point 1, -1. Right, so we're going to allow x to be 1 and y to be -1. And when we do that, we get the vector -2 plus e to the -1, comma 1 minus e to the -1. Right? And so we have our unit vector u, we have our gradient vector at our point, the gradient of f of 1, -1. And so our directional derivative of our function at our point in this direction is simply the dot product of these two vectors. And this is where keeping the scalar out front is actually beneficial to us. Remember, one of the properties of dot products is that if one of the vectors is scaled by a scalar, we could actually pull that scalar out front and take the dot product of the remaining vectors. And so when we do that, we're going to get -2 plus e to the -1 times 2 plus 1 minus e to the -1 times 3. And when you do all of the algebra here, we can write this as 1 over square root of 13 times the number -1 minus e to the -1. Right? And so this is our directional derivative. This would be the slope of the line that intersects the graph of f at the point 1, -1 that goes through in the direction of the vector 2, 3. And as you quickly can imagine, this is much simpler than having to go through the limit definition for the directional derivative that we saw in the previous video. Now in a moment, we're going to look at a picture of this particular example and this particular directional derivative, but I just want to point out before we see the picture that this answer here is actually a negative number. We can see that quite easily if you just factor out a negative from the number in parentheses, and we have a negative 1 over square root of 13 multiplied by a positive number, and so this would be a negative value. So here is a graph of the function that we just were working with, this function x squared y minus e to the xy. So the graph is the thing in blue. We have the point that I'll shade in a little bit darker there in green. That is our point given by 1, negative 1 in the xy plane. And we see that we have our line going through that vector. So this would be the line that's tangent to our surface at that particular point. And again, the slope of that is the directional derivative we just computed, that 1 over square root 13 times negative 1 minus e to the negative 1. Whatever that number is, that's the slope of this line. And I pointed out that it was a negative number. And so what that tells us, the fact that that is a negative value, tells us that at this particular point, if we look at this surface or this graph in the direction of this vector v, we have sort of a downward trend at that particular point. And so if this function were measuring something that you cared about, something on a physics or engineering standpoint, and you cared about what happened in this particular direction, this directional derivative being negative would tell you that this quantity is actually decreasing in that particular direction.